got then? Have we got any attempts at these? Little v at time t. What have you got?
Sine.
Sorry?
A sine.
A sine.
Yep.
So, okay. A sine.
Open bracket. Omega t plus alpha.
Omega t
Plus alpha.
plus alpha. Yeah. Okay.
So I've got 100 sine. 100
Yeah.
cos.
So So let's put that. I'm going to park that up. There, because that's the standard form of a voltage sine wave V at time t. Yeah. So the A. So what you're now going to do, Lewis, is tell me what the A means. What the sorry?
Amplitude.
That's the amplitude.
Peak 100 volts.
So we can pull that from there. That's Lewis's A. 100 volts. Sine. Brackets.
100 pi is the frequency.
100 pi
T
times t
plus 0.
plus nothing because there isn't a phase angle. Yeah? So what you need to be doing here is recognising that that statement there is a sine wave in standard form. So that if you need to, you can pull out these values. Peak voltage, omega, phase angle, in radians. Guys, now, calculators on radians. We're going to be working with radians today, not degrees. Alright? So, the second one here, if that voltage is applied to a 50 ohm resistor, what would be your expression for the current? We know it's in a similar form, so it's going to be something times the sine. It's going to have the same frequency. That can't be any different. It's going to have T. What about the phase angle if that's a resistor?
0, isn't it?
Still 0, because it's a per resistor, no phase shift. So what goes in here?
2.
Yeah, 100 over 50. 2. And that's amps. So there's the volts. So that's an expression for the current. What about the third harmonic? We'll call it V at T, V3 at time T equals, and the magnitude of that is 25 volts, so that'll be 25 sine, what will the frequency be? 300 pi T, and again that's in phase, so that's plus 0 and it's volts. And the last question, what is resonance in terms of frequency and the reactances XL and XC in an RLC circuit? What do we mean by resonance?
They equal each other, don't they? XL, XC, resonance.
Yeah, at the point where it's the frequency FR where XL and XC are equal in what way, Lewis? Because they aren't equal in all aspects.
Value, not
Equal
angle,
in-
but magnitude.
In magnitude still 180 degrees out of phase. Yeah, so they aren't equal in all aspects, but they're equal in magnitude. Yeah, so XL is still a plus 90 degrees or plus pi over 2 radians, and XC is still got a phase angle of minus pi over 2 radians. So all reasonably happy with that revision in terms of what we mean by a sine wave in its standard form. Yeah?
The only thing that I wasn't sure about was the third harmonic. Is that just times the frequency by 3?
By 3, yeah.
Okay.
The fifth harmonic would be by 5, second harmonic by 2, so on. Yeah. Some textbooks call this one the fundamental. Some call it the first harmonic. Means the same thing. Yeah.
Was that in the first exam?
Yes, but in a slightly different way because we were looking at the Fourier series around it. Yeah. But here I'm using it as a way of us looking at analysing AC circuits. So there's a particular topic I want to cover called harmonic resonance. You may or may not get a question on it in the exam.
They got a definitive answer if we may or may not have it in the exam.
I would say may not. I'd say it's not going to be in there.
Yeah, I don't think it's going to be
If
in
it
there.
says may or may not, I'll say it's probably not.
Jesus, can we turn that? Come on.
No,
Oh,
can't.
that's really
Had
good.
that yesterday. I know.
Oh,
Had that yesterday in that room. Can't do anything with it. I can't.
I'm just a bit confused. Let's do
Guess
this.
you don't take all of them. Don't take it soon.
So,
So it builds up that pressure.
Oh, no shit.
Who's it around? I thought it was
Don't mind fire.
Come on, I don't mind.
It's a
There's
case,
no, there's no peace here.
yeah. In case of how many nights you've got on them.
It's a couple.
Just the one today.
You changed them back, mate.
You would as well.
I like that round.
People are what?
Maybe this is not be about.
right. So we're going to have briefly have a look at a circuit with just a plain applied voltage, no harmonic to start with.
What's this topic called then, Mike? Just
So this is AC theory for us
Okay.
still, AC circuit analysis. Calculate I in total XL and XC, total impedance ZT, sketch impedance phasor diagram. Calculate the current. calculate VR, VL, and VC, and prove Kirchhoff's voltage law. How confident are you that you could have a go at that?
Half of
Where
it,
we stand.
probably half of it.
Shall we see how far you can get and then take it on from there? I think that'd be a good way to do it. Alright, so I'm going to pause the video now and let you have video now. Okay, so XL and XC. Hopefully we've been calculating XL is equal to omega L, so that is 200 pi times 0.2 equals, what's the result of that? 126 ohms, or what did you say, Lewis? 40 pi ohms. In actual fact, I'd tend to leave it as 40 pi for ongoing calculation further on, to be honest. It's just easier to handle. And XC, 1 over omega C, 1 over 200 pi times 20 times 10 to the minus 6. What did that come out as? 79 point what, Kyla? So 79.6 then, yeah? For 3 significant figures. Yeah? So there are 2 values for XL and XC. And then ZT, some discussion about it. We'll eventually come up with, I would hope, ZT is equal to R plus XL minus XC J ohms. Yeah? Putting in the figures, resistance was 6 ohms plus 40 pi minus 79.6 J. And then doing a conversion on that.
Oh, I didn't convert it.
So do a conversion on that in with the angle in radians, please. You're going to want that to calculate the current in a minute.
And you convert it to polar.
Convert to polar, yeah.
Just what? Just the bracket.
No, well, the whole thing. So you can put it in one go. You don't need to find an answer to that. Just put 40 pi minus 79.6 after the column. And make sure you're in radians. .46 ohms, angle 1.44 radians. Yeah?
How much you got, sorry?
Put-
Yeah, all of 6, 46 once you went. Not really, so.
Okay? You got all that? Got that now, Carl? Yeah? So, this impedance phasor diagram. Which phasor is the in-phase component of impedance?
The inductor.
In phase, the one at 0
Oh,
angle.
resistor.
Yeah. So we draw R. Six ohms. There. Yeah. You don't have to. If it says sketch, doesn't have to be to scale. But if something is bigger than the other, just try and show that in some way. Which way is XL?
Up.
Vertically upwards. XL, what was that? 100 and 126 ohms. Yeah. Which way is XC?
Down.
79.6. So it's a little over half of that downwards. XC 79.6. Down that way, the negative J direction. Okay? Then what you want to show is the overall reactance X, that's the bit inside the brackets. And I know some of that's 70, Tony had that. What was that difference between the two, Tony?
46.
That's XL minus XC, and that was 46 point what? And then your impedance comes from that. Z is equal to 46.6 ohms, and the angle in there equals 1.44 radians. So that's what I would call a labelled impedance phasor diagram. Remembering that if we change the frequency in that circuit, the length of the red and blue lines are going to change, and it's going to change everything, because X can move up and down, go below the line. Tony.
So, if that's the resultant, Z,
Yeah.
should that not be more than what the XL total, or the X total is?
No, as long as it's negative, isn't it? Is that right?
No, it's not always more. It's if this angle, if resistance was less, that would be much bigger. It ain't never going to be as big as either XL or XC, is it?
No, yeah, that's I mean, because I thought it looks like that's not the scale, is it?
No,
Right,
I know.
then I know.
Sketch is not asking
Yeah.
you to draw it to scale,
That's right.
but I'm asking you if one thing is bigger than the other, that you show that in some way.
So
Do you see what I mean?
Is the 1.44 rad, is that rough, is that about 90 degrees? R6 is quite small.
Pi over 2, 3.14. So pi over 2 radians, 90 degrees, is about 1.5, 1.57, something like that.
So that's why.
So it's quite close to 90. Yeah, because in terms of scale,
yeah,
the resistance line here is over long, isn't it?
yeah,
Yeah.
yeah, that's fine.
So
yeah, that's right.
there's not. I mean, you could argue that those two are almost to scale, but if that is scale, then the resistor line isn't. That would be a tiny little bit there. So yes,
Yeah, so
in terms of that, it is much steeper than is shown on that diagram.
that's why Z is nearly the same
But
as the.
That's not the
Yeah.
important thing I would be asking for if I asked you to do that. It's that you know that XL goes upwards, XC goes downwards. The overall reactance is the difference between the two, and that gives you the impedance phasor at the cross section of those
So
two.
I was just trying to understand why ZT was nearly the same as just the complex or the XL and XC totals,
Because the angle is
because they're
Steep.
the actual
steeper than it
that's-
looks on my diagram.
That's fine. That's
All
all
right?
Yeah, I get
Yeah.
that. So yeah, it's just because it's nearly 90 does make sense because obviously the other two are you've got a big inductor
Yeah.
capacitor, but you've got tiny, tiny resistors, so you've not actually got much real terms of
No.
resistance.
All right.
Yeah.
So you're happy now?
Yes.
Yeah. So we've got an impedance value of 46.6 angle 1.44. We need that on the next page. Let's take all that. Park that up there for reference. Calculate the current, VR, VL, VC, and prove Kirchhoff's voltage law. Can we have a go at that? I'll have a go at that. Starting video again now. Okay. How do we calculate current? I is equal to V over Z. V in this case is no angle, so it's 150 angle nothing, divided by 46.6 angle 1.44. How do we do that polar arithmetic?
Real and imaginary parts separately.
Sorry?
Do the real and the sorry, the
The magnitude and the
angle.
angles separately, yeah? So what do we do with the magnitudes?
Divide the real and minus.
And subtract the angle, yeah? So it's 150 by 46.6. 3 something. 0.22 amps angle minus 1.44. Yep.
Yeah.
Okay.
Got that bit.
So moving on from that, how do we calculate VR?
The total current times the resistance.
I times R. I is 3.22 angle minus 1.44, and R is 6. No angle. So how do we multiply those two numbers?
You have to convert that to.
No. Look, if I make that 6 angle nothing, do you know how to do it now, Luke?
You just times
Multiply those two.
and then.
Add the angles. Yeah. So 6 times 3.22 is 19. 19.3 volts angle minus 1.44. Yeah, maybe. If you don't include the degree symbol, actually radians are implied. But VL, I times Tony. For VL, I times XL. So we are 3.22 angle minus 1.44 times 40 pi angle for an inductor in radians.
20 degrees.
That's 90 degrees, isn't it? But radians.
90 degrees in radians is
2 pi.
2 pi is the whole circle, 360 degrees. So 180 is pi, so
two.
90 is pi over 2. So 3.22 times 40 pi. $405 to 3 significant figures. Do you agree?
Yes.
Angle.
Zero.
0.131. So you've got 405 volts across our inductor. VC is I times XC. 3.22 angle minus 1.44 times, and that was 79.6 angle for minus 90 minus pi over 2. $256. Volts. Angle. Minus 3.01, yes, yeah, great. Okay, so Kirchhoff's voltage law wise, if we look at that, we're saying we got 19.3 volts, 405 volts, 256 volts. Adding all them together certainly do not make 150, does it? So what do we need to do?
Take into account the angles.
Yeah, so what's the easiest way to do that? We've got to add them all together, yeah, convert them back to rectangular form. So in rectangular form, R equals, VR equals, VL equals, VC equals, and then add all them together, and you should find that you get 150 volts with no angle. So you've got to collect, we've got all these polar terms now into rectangular.
VR was
Yeah, it's not
positive
minus,
angle.
You got the wrong way around.
We've got a negative angle.
Thought it was positive.
90, the voltage
Negative, yeah.
is negative.
And
19.3 negative. So just to clear up, in our diagram we're talking about a vector that is 19.3 and the angle is down there. So we're expecting a positive real part, 2.52, and a negative j part.
See, I had
Do you agree?
VR equals 6 angle 0 times 3.22 angle minus 1.44.
Yeah,
But then I added the 1.44,
to 0.
which give
No, yeah, but you've got to add minus 1.4, remember. Care with your addition, subtraction of signed numbers, Carl. It's 0, or it's minus 1.44 plus 0. What does that leave? Alright? Agree with that one, Lewis?
Yes.
Yeah.
Move the matching parts separately.
Just add
Yeah, so they are all those. Do you agree with the last one, Lewis?
Yeah.
Yeah. So they are all those. We just add up the two columns separately. So we do 2.52 plus 402 minus 254 150.52, so as near as down at 150, allowing for the fact that we're converted twice. And what should happen with the J parts?
0.
Minus 19.1 plus 52.9 minus 33.6 equals which is approximately equal to 150 plus 0J volts. Yep. Remember doing that? We've done that in science for sure in the first year, let alone earlier this year. Okay? Right, Carl?
Yep.
Luke? Tyler? Yeah? Tony? Lewis?
dark.
All happy with that, yeah?
VR.
Right.
Is that the last part through KVL?
Yeah, that's proven KVL, that is, because we've proved that we're actually got across all, if we add the voltages across all three components together, we get the supply voltage. Tony, yeah? Alright? 150 volts. Okay. So, what we're going to look at now is where we get a harmonic. So we get a voltage and we get a voltage where we've added a harmonic to it. So we're going to look at a circuit where going to start off with a resistor and a inductor in series. We're applying a voltage that's got a fundamental 400 sine 100 pi t. Yeah. So that just happens to be 50 hertz, like 50 hertz mains. So you get the frequency from just dividing that number in front of pi by 2. And added to that is a fundamental of 130 volts magnitude, 300 pi t. So it's the third harmonic. Neither of them have got phase shifts involved with them. Okay. What we're going to demonstrate is that you can analyse these circuits by analysing each of the waveforms separately. So you can analyse the current due to the fundamental and the current due to the third harmonic, and add them together, and you'll have an expression for the current, the total current flowing in the circuit. Okay, so calculate fundamental and third harmonic frequencies in hertz. It's the first thing I'm going to do. How would we do that?
Is that the resonant frequency formula?
No. At the moment we've got two. What have we got in there as far as frequency is concerned? What form is our frequency in? You see, radians per second, it's in what form? Been working with it.
Omega.
In omega form. So we've got omega 1 and omega 3. Yeah? So what we can do is say omega 1 is equal to 2 pi f1, the fundamental frequency in hertz form. Therefore, f1 is equal to omega 1 over 2 pi. That's 100 pi over 2 pi equals 50 hertz. Yeah, like I just said, glibly, it's the number in front of the pi divided by 2. So omega 3, 2 pi f3, therefore f3 is equal to omega 3 over 2 pi, 300 pi over 2 pi is 150 hertz. So fairly simple, but if you're asked to do that, you need to know that omega's in that standard form equation there. The two omegas are in there and with what it is. It's called understanding the electrical theory behind all this maths. Yep, what the numbers actually mean. B. Calculate XL and XL only got XL at the moment at omega 1 and omega 3 frequency. So how are we going to do that?
Convert it. Oh, we got it inverted actually. So yeah,
You don't
2 by
actually
FL,
need it
isn't
in hertz, do you?
2 by FL.
Yeah. But do you need to convert it to hertz? I've asked you to do it
Right, you don't need to.
in the first part of the question, but
Can
Do you
just
need
do
it in that
omega
form?
L
yeah,
and,
Yeah,
1 over
of course you
omega
can.
2?
yeah. So you can do XL1, XL at omega 1 is equal to omega 1L as 100 pi times, and I ain't even given you component values yet. Your inductors 50 millihenries, so 0.05, I'll put them on the diagram in a minute, equals and XL3 is omega 3 times L 300 pi times 0.05 equals. And the resistance is 1.5 ohms, and I said that was 50 millihenries. Leave it in pi form at this moment in time. What we got? 5 pi for the top one and 15 pi, 3 times it for the second one.
I've got 50. Yeah. 50.
50.
God, this is
Oh, for your first one.
yeah.
Definitely 5 pi the top one. And 15 pi. So a wrong button pushed somewhere. You got 50. Calculate Z1 and Z3 so that impedances at the fundamental and the harmonic frequency in polar form. So how are we going to do that?
Is it R plus XL1?
Yeah? What you missed off there, Carla? Very important thing off the end of there.
What's value for
J.
J. Yeah? Must not forget that J. Complex number. Alright?
that? What was the value for that?
1.5 Carl. Throw me the polar conversions when you've done them. We got this.
15.78.
So 15.8.
Angle 1.48 radians.
And there's ohms in there. And the bottom one
47.15 ohms.
is 47.2 ohms, angle
Angle
1.54 radians. Does that make sense, the angle getting bigger when the frequency goes up?
1.54. Yeah.
Yeah, because you think of the diagram, we've only got an XL on the diagram here. So this is the diagram for omega 1, XL up there, R in there. There's our impedance. Yeah. Over this side for omega 2, the XL line has got bigger. That line stays the same length, so you would expect the angle to become steeper. Yep. XL1, XL3, R and R. Alright? Lead. Bigger angle, smaller angle. Alright? So happy with that, yeah? D. Calculate I1 and I3 and write expression for I at time t. Have a go at that. I'm going to pause the video now. I'm going to stop this one and start again afterwards. Okay?